Today we are going to learn about electrical conduction. So what do you mean by electrical conduction? It is nothing but the movement of charge carriers, that is prominently the electrons, through a conducting material. Right. Before we start, I have a question. Can you imagine a day without all these electronic gadgets that are displayed here? Say it your mobile phone, television, even the projector, and whatever you use in your day to day life. I don't think so. If you say yes, then you give it a thought. Is it real? If no, then better understand the science behind it. Science helps in the growth of technology, and we could not imagine a life without technology. They both go hand in hand. Now, how is this feasible? Just imagine or just think about what is inside a laptop. As displayed here, you could see some kind of green color board with lines over it and few components here and there, basic electronic components like capacitor, resistors, diodes, etc. Right? And can you imagine each of these components inside have a significant role, and even the lines, the copper lines inside has its own role. Now, these electronic components in a circuit can be classified under three broad categories. First one is the conduction path, and then the voltage source and the load. So coming to conduction path, it is nothing but the traces of copper that you find on the PCB board. Here the current flows through these conducting path. Without these copper traces, the PCB board is nothing. And the second one is voltage source. If I want my laptop to work, I need a battery. That is, it helps in providing a potential difference between 2 points in a circuit that helps the current flow through it. Right. The third one is the load. Load can be as simple as a light bulb or an LED bulb, a capacitor, all those things. Now you can see each of these are made up of different type of materials. So coming to electronic materials, the novel polymers exhibit semiconducting behavior. Can you imagine about it? And the electronic materials play a key role in development of computer based and information based technologies. For example, just you most of you would have used the touch screens. Even in the watch, the fitness watch which you use has the OLED, organic LED display over it. You can just make the display work by a touch. And this is made up of organic material. And then just imagine the fuse carrier. There you could see there is a copper wire inside, which is nothing but a conducting material, and then you have porcelain on the outside, which is a completely insulating material. Can you just imagine switching over these two materials? Porcelain inside and copper outside. Wow. Yes, here is where you should gain knowledge about the materials. I mean, this knowledge on the electrical properties of materials will help you effectively select and use the material for a particular application. And the electrical conductivity varies with the type of materials. This is very important. You know why? Because say in this era where we make use of computers and gadgets for each and every application, we keep on revising the software. And when you go for an improvised version of a software, remember you need a hardware that would equally support the software. And this hardware is nothing but all these electronic components that I have been talking in the previous slides. And these components has to be upgraded now and then. How do you upgrade these components? By playing or working with the materials. That is why the knowledge on electrical conductivity of different types of materials would play a significant role. Now, how do you classify the materials based on their electrical conductivity? Prominently, you can classify them as conductors, semiconductors, insulators, and of course, lately, superconductors. Now, coming to your basics, that is Ohm's law, V is equals IR. V is the applied voltage, which is nothing but the product of the current multiplied by the resistance offered by the material. So, this resistance R of the material is not its intrinsic property. R resistance varies based on the object geometry. There is another one which is electrical resistivity rho, which is an intrinsic property. Now, how is this electrical resistivity related to the resistance of a material? That is given in equation 2. You could see resistivity is nothing but electrical resistance of the material multiplied by the cross-sectional area divided by the length of the object. The next parameter is the electrical conductivity sigma. This is nothing but the reciprocal of the electrical resistivity. That is 1 by rho, nothing but L by R multiplied by A. So either of these two, that is conductivity or resistivity, can be used to classify the materials based on their electrical property. Now, these are the values, conductivity values of some of the materials, say conductors. It could go till 10 power 7 ohm meter, the whole power minus 1. Or for semiconductors, it could be 10 power minus 6 to 10 power minus 4, and for insulators, it is greater than 10 power minus 10. So see the value of conductivity, it is high for conductors obviously, which are the prominent charge carriers. Now, what happens when current flows through the material? Definitely, there is some resistance offered by the material, and there would be some loss, power loss. This is given by Joule's law. Power is nothing but V multiplied by I. Joule's law says power is nothing but I square R. There is some loss due to the resistance offered by the material. Now going back to equation 1 and equation 2, that is Ohm's law and the equation on conductivity, and combining these two, we end up with the equation J is equals sigma E. Here J is nothing but the current density, which is nothing but current per unit area, I by A, and E is the electric field, which is nothing but the voltage divided by the length of the material. Now, conductivity, we can also determine the current density based on J is equals N, number of charge carriers, multiplied by the charge on each carrier, Q, multiplied by the drift velocity. Drift velocity occurs as a result of an applied electric field. From equation 4 and equation 5, both of these gives the value of current density. So combining these two equations, that is 4, which is nothing but J is equals sigma E, and equation 5, which is nothing but J is equals NQ multiplied by the drift velocity, we can get the mobility. It results, this combination of these two, equating equation 4 and 5, gives you sigma E is equals, if you look at the right side, sigma E is equals NQ multiplied by the drift velocity. So sigma is the conductivity, which is nothing but NQ multiplied by drift velocity divided by the electric field. So now this value, drift velocity by electric field, is given together as the mobility of the charge carriers, which is nothing but mu. So sigma is equals n q mu. So coming to the conductivity here, you could see that the conductivity depends on two different aspects, that is the number of charge carriers and the mobility of charge carriers. So mobility is important for metals or electrical conductors, whereas the number of charge carriers is important for semiconductors and insulators. So if you look at metal specifically, you can keep sigma as it is. Sigma is equals n q mu. For semiconductors, the conductivity sigma is equals n q mu suffix n plus n q mu suffix p. So here you could see that we consider both the charge carriers, that is electrons and holes, because semiconductors can be of both p type as well as n type. Whereas for ionic materials, it is entirely different, where we see the total conductivity will be equal to the electronic conductivity plus the ionic conductivity. So having understood a little about the conductors here, let us just try to solve a problem. And you're just give it a try, check whether you're able to solve it. A specific application requires a 2 millimeter diameter by 1 meter length wire with a high conductivity. So we are talking only about the conductors here. There are two available options: an aluminum alloy, a copper alloy. And through each of these, we are going to pass a current of 5 ampere for testing. The measured voltage drops in both these cases are given. For aluminum, it is 215 millivolt. For copper, it is 80 millivolt. The question here is, which wire would you choose? See you again with few more problems to solve. The next topic will be on electronic and ionic conduction. Here I'll be focusing a little on metals followed by ceramics. Hope it was useful for you. Thank you.